So, sir, may we start?
Yes, yes, we can
Yeah, thank you.
start.
Yeah, good afternoon, sir, and good afternoon, all the dear participants, and welcome all of you to the third session of the second day after this lunch break. This session is going to be taken care by Dr. Arvinda S. And let me introduce the speaker. Dr. Arvinda S. is currently posted at Indian Institute of Technology, Tirupati, in the post of Assistant Professor in the Department of Physics. He receives his PhD in, from Purna Pranja Institute of Science Research, Bangalore. Bachelor's degree in Basic Sciences and completed Masters in Physics from National Institute of Technology, Karnataka, Surat. Area of interest in the field of quantum information and quantum computation, quantum foundations, quantum information theory and computation, quantum many-body theory, quantum chaos, etc. In present investigation of the ubiquitous occurrences of entanglement in various physical systems, Dr. Arvinda S. has contributed in several praiseworthy contributions. Sir, we are eagerly waiting for your esteemed lecture with no further delay, and most importantly, thank you very much for accepting our. Over to you, sir.
Thank you. I am very much thankful to the coordinators for inviting me to this lecture and asking me to present this lecture. And if any first thing, if any interruption in the internet or other things, if you are not clearly audible or other things, please inform me. That's the one request. And today I will be going to speak on multipartite quantum entanglement. And in this, if you I'll start with the plan is that I will start with the two body entanglement or two particle entanglement, and then slowly go to the three party, four particle entanglement, and what is the current research is going on, and in relations to physics systems and also in relations to quantum computational models where it is going to be applicable and all other things. Starting very basically starts from the very original motivation, like when Einstein started, what happened, and all other detail. If you stuck at any place, if you have any questions and other things, you can stop at that point. If it is a technical question to answer, I try to explain at that moment. If not, if it is some conceptual, I will try to conclude at the end and take the questions at the end also. So let Jainji, so what is the format? Means 1 hour talk and 15 minutes discussion, or what is the way you have any suggestions for that?
No, sir, you can stretch it up to your convenience.
Okay, thank you. Okay, let's begin. We all know, I think you have already heard that who have little experience in quantum information theory or the quantum computation, the very basic ingredient of quantum computation is the entanglement, what we call the entanglement, which plays a central role both in quantum information and quantum computation. In some sense, without quantum entanglement, none of the information theoretic protocols or have greater significance compared to classical systems, or even the quantum computation. For the quantum computation to succeed, its supremacy over the classical computation, in the sense that there exist some protocols for which quantum computation outperforms the classical computation. A basic ingredient required for such process is entanglement, basically the quantum entanglement. So where does the story start? All this, the story started from Einstein, famously a debate started in the very early 90s, like 1930s. After the completion of the formalism of quantum mechanics, there exists a body of quantum formalism where the theory is formulated in a well-defined mathematical terms, whereas the interpretation, what this theory is trying to tell us about nature's nature, was the questionable. At that point itself, in the 1935 itself, the concept of entanglement in some sense started. With the famous paper by Einstein, Podolsky, Rosen, today what we call the Epr paradox or Epr paper, where he asked, can the quantum mechanical description of physical reality be considered complete? And then replying to that, in order to answer those questions, is the idea as well as the concept of entanglement began. And the second, what is the most basic origin which today's quantum information theory or the quantum computation is enjoying, it comes from none other than John S. Bell, which what we today call the second quantum revolution. He famously put forward the theorem which we today is called the Bell's theorem, which says that no local realistic model is compatible with the quantum mechanics predictions of the quantum mechanics, is the second term which taken place around 1965. And then I would say the birth of the quantum computation is by when David Deutsch wrote his first algorithm, Deutsch algorithm, in 1985, where his basic motivation was different. In order, he wanted to prove one of the interpretations of the quantum mechanics, but he came up with the quantum concept of quantum computer. Of course, Feynman had some idea, but the Feynman's idea was a simulator, whereas the Deutsch was able to come up with a proper notion of the computer. That I would say that the beginning of quantum computation. And then started I would say the quantum information started with the teleportation by these famous six people, Bennett, Brazard, and Claude, Joseph, Perez, and Wooders, where they come up with the protocol to teleport an unknown quantum state by using the entanglement, where entanglement is necessary for a quantum teleportation, which no classical system can do these things. So that's where the quantum information science began in some sense. And where are we? Today we are in what is called NISQ era, noisy intermediate scale quantum computers. Of course, this is 2018, already 4 years completed when Preskill wrote this article, and we are in a our development is in this idea is huge. For example, where are we standing now? If we ask, so there is a recent paper. Can you mute it? Yeah, okay. So today, where are we standing? There is a one recent experimental realization by Weipan, and which says that there is a classical, there is a one task for which the classical algorithms takes 4.8 into 10 to the power of 4 years to solve. This is the time scale for the classical, whereas in the quantum computer, what they developed called Zoom Z 2.1, it took just 4.2 hours. This is the time scale difference between the classical and quantum computer today we are in. Okay, so in order to begin, if we ask what is quantum mechanics, or in other words, what is a theory? So, in a quantum mechanics, let us imagine there is an experimentalist who is entering he is doing an experiment, and there is a theorist who enters into the experimental lab, and he asks that is it a quantum state? So what experimentalist is having a table of contents where only the probability distribution is being given. He has only probability distributions. From the probability distribution, so this is an operational theory because in the lab they have done and got the probability distribution. From the probability distribution, one has to construct the theory. So what are the basic ingredients of the theory, or in other words, what is the basic ingredients when the experiments begin? Is that one begin with some state preparation. That means, for example, electron in some spin up position or spin down position at some property. Remember that here in quantum mechanics, every operator, every Hermitian operator is a physical quantity. So let's with some physical property, some Hermitian operator, some eigenstate of an Hermitian operator represents some physical quantity. So prepare that physical quantity state in a laboratory and then transfer. You have the knobs and other things, and then transfer and then make a measurement. And through that measurement, one will be getting the probability distribution. So this is what happens in the experiment. For that, one has to make a representation in a theory. The states are represented as a vector in a Hilbert space, and the operators are represented as Hermitian operators, and the probability distributions are given by the Born rule. So this formalism of representing operational statistics through a mathematically, that a state living in a Hilbert space and an operator which is Hermitian operator represents which represents the physical properties, and the transformation is represented by unitary evolution, and the probability rule is governed by Born rule, is what constitute the quantum mechanical framework. So the quantum states, which is what very fundamental. So states are represented as a vector in a Hilbert space, and this is a single party state. That means only one system is there, one electron, for example. And what the state represents? State represents all the information. In state is a mathematical representation in which all the information about all operator statistics is invoked. What does it mean? For example, for this state, if sigma x is measured, what is the probability distribution of getting spin up or eigenstates of sigma x is 1 by 2, 1 by 2. If instead of sigma x, sigma z measurement is made on this state, what is the probability? It will be 1, 0. Always get the 0. Or sigma x, if the sigma x is being made on this state, what is the probability distribution we are going to get? That means given any experimentally possible observable, if such a possible observable, the measurement is made on this preparation, all the probability distribution is encoded in this mathematical state. This is what represents the state. And the beauty of this quantum mechanical formalism, if it is in the classical, either 0 is possible or 1 is possible, or any one of the state is possible, whereas in quantum mechanics, all possible superpositions are possible. So this is the most general state, most general pure state, which will be represented. This is single particle quantum state. Now let's move to bipartite. That means two-party system. That is, let's call the system A is one and system B is another one. So there is the one system A, means there is the one single electron at position A, you can say, for example, in Tirupati, and another one could be in Tripura. That is what the system B. So what is the Hilbert space? Hilbert space is the tensor product of two systems, and this is the representation I am writing. If I am writing in between, this also represents the two systems, the tensor product. So 0, 1, 0, 1 is the tensor product, get 0, 1. This is what the state representation of the bipartite state. And with the bipartite state, there are two things are possible. One way to write is in this way, another one is the superposition. So if the state can be written in this way, what is its mean? It is called separable. What does it mean? I will come to this one. And if you cannot write it like this, then this state is called the entangled state. What happened? So there are many ways to explain the entanglement, but here let's try to explain the entanglement in this way. I'll try to explain the bipartite entanglement and then go in some detail. In this example, suppose at A, that means at Tirupati, for example, and another system is given to you people who are carrying with you in Tripura. And if you at sigma A, at system A, that is at Tirupati, if sigma Z measurement is made on this system, and if we get 0, then definitely I will know that if you made the measurement sigma Z at your place on your system, you will get 1. So one way of understanding this one is that perfect correlation. There exists a perfect correlation between the measurement outcome of one party to measurement outcome of other party. That's not enough. The perfect correlation exists for every measurement. That's the beautiful thing of the entanglement. It's not just sigma Z. If you measure sigma X also there exists a correlation. If you measure sigma Y also there exists a correlation. So that correlation exists for any measurement. This state cannot be written simply as a tensor product of two states. If you cannot write, those states are called the entangled states for the bipartite system. Let's little bit move forward to give some concrete definition. For example, if system A and B, if you can able to write it like this, there is a tensor product of two states, then it is called a separable. If you cannot write it as, then it is called the entangled states. In order to explain more efficiently, I would like to define two aspects. One is the density matrix, another one is the partial trace. These are the two concepts which I need to explain. So what is the density matrix? When we have two systems like this, so there is a system A and there is a system B, and which is preparing two states. Let's say this is the one state psi 1, it is preparing some state psi 1, and this is preparing state psi 2 with some probability distribution. Imagine this is the probability distribution 1 by 2, this is probability distribution 1 by 2. What is the most general representation of the state preparation of this state is written as in the density matrix. Density matrix representation is the most general representation of the states, which is the trace of the density matrix is equals to 1 and it is a positive operator. These are called the trace class positive operators. This is the one concept which is needed, which is called the density matrix. And other thing is called partial trace. That means I am tracing out the second system. If I am able to trace out the second system, how to trace out the second system? So trace is the reduced density matrix. What is the reduced density, reduced state of the system? Then there is another definition for a pure state. That means rho B is a pure state. Pure state is that the states which you cannot be able to write as a mixture. If you, these states, if can be only written like this, then these are called the pure states. If you cannot written in this form, then these states are called the mixed states. If the combined system, the rho AB, is pure, whereas the reduced density matrices, reduced systems are mixed, then it is called also called the entangled system. What does it mean? The combined system, so there is the full-fledged information in the combined system, whereas if I only look into the small system, single system, no information is encoded in that system. That's what one way to define the entanglement. And the quantification exists. So the quantification is very famously quantified using von Neumann entropy. This is von Neumann entropy. So where this how the entropy is defined, trace of rho a log to rho a, where rho a is the reduced density matrix, which takes the values from 0 to 1. If it is a pure state, if the reduced density matrix is pure state, then it is equals to 0. From that you can conclude that the state is not entangled or entangled. Let's take a famous example, which is the Bell state. This is called the Bell state. There is the two systems again, A and B, which is well separated spatially. You know this. This is the state called the Bell state. Whenever 0 0 plus 1 1, and rho A or rho B is maximally mixed state. So if the reduced density matrix, the reduced state is a maximally mixed state, then the combined state that or the two-party state is called the maximally entangled state. Bell states are the maximally entangled states. Let's make some generalizations. I will be little bit sorry to say I will be taking some little expanding the things more rigorously using some mathematics and other things. You could just I would like to give the mathematical essence and what's happening in these systems also. With some generalization, any state, two-parted state, if we can expand it in the computational basis, and let's define A is a operator with this computational basis, Aij elements, you write it as an operator. So this is called the vectorization. The easiest way to understand is that, for example, let me try to explain it. So easiest way to explain it, for example, you have A, B, C, D, this is the vector, and then make it a operator like this, A, B, C, D. Okay, this is what is called the famously vectorization, and from that the reduced density matrices can be obtained, which is nothing but A dagger and A transpose A. And there is one more concept called Schmidt decomposition, and how many Schmidt values will quantify whether the state is entangled or not. This is about the bipartite entanglement. I will be now slowly going to some concepts and then some physical base. So now till now what I have explained is the mathematical feature of how to characterize and what is entanglement and other thing. Now I will be next I will be explaining Epr paradox and Bell experiment, which is focused only on the bipartite entangled state, and further I extend it to 3-party, 4-party, and what mathematics and how the computations emerges. Till now, any questions? If you have any questions, please let me know. Okay. Now, let's try to understand the very motivation when Einstein started this concept of entanglement and all. It started with this paper, the wonderful paper. The title of the paper is Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Hello, am I audible?
Yes, sir. Audible.
Okay, thanks. Yeah. So in this paper, they come up, there are the two terms to understand here. One is quantum mechanical description, which I have already explained what quantum mechanical description means. And there are two more words. One is physical reality. What do we mean by physical reality? And what do we mean by considering something complete? Okay, so all these sentences is copied from the paper. These are exact their words, not mine. they says that in attempting to judge the success of a physical theory, we may ask ourselves two questions. Is the theory correct? That can be checked in any experiment. So there is a theoretical prediction. You have made the theory, you have constructed the mathematical formalism of a theory, and after that, that one can come up with the predictions of that theory. And then once we know the predictions of the theory, just go to a laboratory and do an experiment, check that whether the theoretical predictions are in accordance with the experiment. If it is and no other experimental evidence is found which disproves the predictions of the quantum mechanics, till that the theory is correct. Next, is the description given by the theory complete? This is the question they ask. Then, what do we mean by requirement? They come up with the requirement for the completeness of a theory. The requirement of the completeness of the theory is necessary one. That means every element of physical reality must have a counterpart in the physical theory. What does it mean by? So you have seen some physical reality. That means I am speaking. You are able to see me. So suppose you associate a physical reality to me or my speech, then if there is a theory which you are going to develop on my speech, then that theory should associate an element of physical reality. More simply, let us what happens in the classical mechanics, there is a position and momentum. This position and momentum of a particle is the realistic value which you are aware of that. So this is the position and if this is the speed with which it is going on. If that is the case, in that cases, the classical mechanics or any physical theory should take into the consideration, take into the account of this physical reality into their mathematical framework. Then the second question, next question asked. So how do we know what is the physical reality? They come up with an answer. If without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to the that physical quantity. That means, suppose if I am, so you are in you see there is a room. In that room there is a chair and room is locked, nobody is inside in the chair, and you open the room and you enter into the room. Okay, the chair is there, so the chair's position nobody has disturbed, so I know its position precisely, though that means that there is an element of reality to the chair's position. This is what they claim. This is their definition to begin with, Einstein, Podolsky, Rosen, to start with. Then they come up with this beautiful experiment. So there are two people, Alavelu and Babu. So there is an entangled state created in Bangalore. Somebody creates that entangled state. In one of the system, there is one of the electron is being given to Alavelu, and another system is given to Babu. Babu flies to Tripura and Alavelu flies to Tirupati. Both are spatially separated, but the state is prepared in this state. You spin up and spin down, spin up and spin down. Now, if Alavelu makes the measurement sigma z, and if she gets up, then definitely Alavelu know that if Babu makes the measurement in her system, in his system, then he will always get the down. But Alavelu has not disturbed Babu's system. So without disturbance, Alavelu is able to know what is the state of the Babu system without any disturbance. Then according to the criteria, a physical reality can be assigned to sigma z. Similarly, sigma x measurement they can make, and even for this state, again if sigma x is measuring, if Alavelu gets the sigma one of the value of sigma x, then it, since because of its correlation, Alavelu would know what value will Babu gets once the Babu makes the measurement. Then without any disturbance, Alavelu is able to guess that with certainty Therefore, a reality can be assigned to sigma x also according to the EPR criteria. But quantum mechanics says that this cannot be jointly measurable, non-jointly, not possible to measure jointly. Therefore, they conclude that there exist realistic values for both sigma x and sigma z, but quantum mechanical prediction is not allowing for the for the joint measurement of these two operators. Therefore, therefore the quantum mechanics is incomplete. In their statement, while we have thus shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. This is what the statement they come up with in around 1935. This is famously called Epr paradox. Then there are many people who try to complete the theory saying that there is some hidden variable which we don't know. So what is this hidden variable? What is this concept? I will be coming to that. But before that, for example, if I am tossing a coin toss, and the outcomes of the coin toss can be head or tail, we don't know. That's completely random. But suppose if I am able to know all the parameters, like to what is the speed with which I toss the coin, and what is the wind speed, and everything, given all those additional data, it is always possible to calculate the outcome precisely, deterministically. Another example is some mathematical function, random number or other things. You all know that. If you don't give that function, then it appears to be completely random. But if you know the function with which the random number is generated, then obviously I would know what is the outcome which is going to come. That is, it is deterministic. Giving that extra information is what is called the hidden variable. And Bell in 1935 come up with one experiment. Again, the same previous situation. Alavelu is carrying her system and Babu is carrying her system, his system, and they have two measurements, A1 and A2, and B1 and B2, like sigma x and sigma y or sigma z, and each one is having plus or minus one eigenvalues. And for one system, they make a measurement and they get the outcome. And then another system the referee will send from the Bangalore. So they do the experiment again. So repeatedly they do the experiment, and then they got the they get the joint probability distribution. So this is the joint probability distribution of two observers. There are three assumptions which John Bell makes. Here lambda is what is called the hidden variable. The first assumption is called determinism or realism. That means even though if it is random, for example, coin toss or other things which you don't know, which you cannot predict randomly, but it exists before my observation deterministically. For example, coin toss, if I toss the coin and get the head or tail, before I got the measurement outcome, the value exists. The assumption that before my observation it was there is what is encoded in called determinism, that this joint probability must take either 0 or 1. Famously, there is one quotation by Einstein. He was walking on the road and asked that, is there a moon if nobody looks at it? So this, if without, for example, take the idea that which I explained just now, that there is a room and there is a chair. Inside the room there is a chair, and you open the room and enter and you see the chair. So before you open the room, was the chair was there at that? It is there before my observation is what is called the realism or determinism. This is how the classical world works. Okay, so that's the one assumption. And another assumption is local causality. That means no information can pass instantaneously from one place to another place, which is encoded mathematically, saying that marginal probability distribution of Alice or Alavelum or Babu should not depend upon whether the measurement, what choice of measurement Babu takes. Okay, what I mean to say is that if in the first equation, whether Babu takes B or B prime, the probability distribution of Alice should not be get affected. Similarly, the Babu's probability distribution, that is local marginal probability distribution, should not be get affected by what is the choice of the measurement observable by the other part. This is what is called the local causality, or no instantaneous transfer of information. Another assumption is measurement independence. That means the measurement choices are not influenced by the hidden variable itself. Why this is important? This is what is our classical intuition says. This is what is our classical mechanics is. In some sense, this is how the classical computer is working. What is the fundamental difference? That question, what is the fundamental difference between the classical mechanical understanding and the quantum mechanical understanding? It is not in the mathematical framework. In one is a Hilbert space, another one is phase space. That's not. There is a fundamental difference between our understanding of these two formalisms. That's what is captured initially by the Bell. And he derived an inequality, a mathematical inequality, from these three assumptions: determinism and local causality and measurement independence. This is also called free will, implies the Bell's theorem, Bell's inequality, implies the Bell's inequality. And the Bell's inequality is the expectation value of A1, B1, A1, B2, A2, B1 minus A2, B2 must be less than or equals to 2. This is what Bell's inequality is that, and this inequality is completely violated in quantum mechanics, and in quantum mechanics it goes up to 2 root 2. What does it mean? Since negation of the Bell inequality implies either the negation of determinism or either the negation of causality or either the negation of the measurement independence. So what are all the advantages of this one? Why I am coming and explaining it here in the quantum computation class? Because if the random numbers are generated from by using the violation of Bell inequalities, then that randomness is device independent randomness. Means there is no mathematical function, or nobody in the universe can know what is even before, what was the value before the measurement. It is truly random. So that provides that justification of true randomness comes from the Bell's inequality. The whole formalism is based on this one. These are called the device independent framework, the framework in which the probability distributions are there, and based on that probability distribution you will be construct the entire protocols, quantum information theory protocols, or randomness generation and everything. So for that purpose, It is important. The violation of determinism. What does it mean to say that before my measurement, before my observation, the values were not at all existed. So my, in some sense, in a very crude English, my measurement created that values. So nobody knows that. So it's a completely random. Nobody can know that. So that's why it produces a true randomness, which is what you can use it to encode your information and passwords and OTPs, blah, 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 all these things which generates this, and which is the very core essential of cryptography. What it says that quantum cryptography, device independent quantum cryptography, in some sense, what it says, nature provides the security. It's not, security is not based on some composition of some mathematical framework. That's the important thing. And there are some extensions one can in order to understand, even to extend the quantum mechanics, there are something called indefinite causality and quantum gravity approach, both from the physics, and also this indefinite causality gives much more quantum computational advantage beyond quantum mechanics, also beyond quantum computers also. Where does this come from? All these things in some sense has the origin in the Bell's inequality. Okay, so this is about the two-party entanglement, and I will next go to the multi-party like 3 and 4. So, sorry, is there any questions until now? You can ask. No questions? Any questions, or can I proceed? Is it, am I conveyable something what I am explaining?
Yes, sir.
Okay. Thank you. Thank you. Okay. Let's go to then, if that is the story about two parties. I'm again reiterate, now onwards also it will be more, I will be using more mathematical terms, no more big slides of explaining what it is and all other things, but it will be more mathematical. And that's what the crux of quantum information and quantum computation is hidden. Let's go to three parties and then what happens to higher number of parties. We know that in the Bell state, there is a, like this is the Bell state which we began with 1 by, here it is there, okay, sorry, the Bell state which I have begun. This is the state, the two-party state, two-party entangled state, for which every single party, rho A and rho B both are pi, okay, in general, if I extend it, so rho A, which is equals to rho B also, is pi by 2. If I extend it to any higher dimensional also, so rho A or rho B will be I by T. That means it is completely mixed state. The reduced density matrix of the bipartite state is completely mixed state. Such a state is called the maximally entangled state. Now, suppose if I extend it to three party, this is famously called the GHZ state. This is three party state 0, 0, 0 plus 1, 1, 1. So, for example, A, B, C, there are the three people in the three spatial locations, three different spatial locations, and with the three different spatial locations, they are doing an experiment, and this is also very useful in many quantum information protocols. And if you see that any of the local states, rho A or rho B or rho C, which will be equals to simply I by 2. That means any bipartition like A versus BC or B versus AC or C versus AB, this bipartite cut, these are called the bipartite cut. This bipartite cut is maximally entangled. A versus BC is maximally entangled, B versus AC is maximally entangled, A versus C versus AB is maximally entangled. Now, if we have the n-partite state, then if there exists n-partite state, if all of the n by 2 cuts is entangled, all, what I mean by all, if I am having a 4 party A, B, C, D, AB versus CD, AC versus BD, like that, all the bipartite cuts are maximally entangled. That means the reduced density matrix corresponding to that cut is maximally mixed. Such states are called AME states, AME, absolutely maximally entangled state, and it is denoted as n comma d. N is the number of parties, d is the dimension of the local system. That means here it is qubit qubit entanglement, here it is qubit qubit entanglement. And these AME states are again useful in teleportation, secret sharing. This plays an important role in error correcting codes. For example, it's the famous 5 qubit error correcting code and 7 qubit error correcting code. All are AME states, and it has to be AME in order to protect the states. So, a main entry into the error correction codes, which protects the information in the quantum computation, begins from the entangled state, and the entanglement must be maximum. So that is being quantified in terms of absolutely maximally entangled state. We will deal this thing in more detail in 4 party state, and we'll connect this information to some other domains, for which I need an information called operator state isomorphism. So what is the, I already given operator, what the operator state isomorphism is, which is nothing but a vectorization. That means I have a vector, and this vector can be written as a matrix. So 1, 2, 3, 4. In some sense, 1, 2, 3, 4. This vectorization, in some sense, is termed as a given an operator xc. How do I write this vector? This is an operator is living in a Hilbert space of dimension d, and the vector, how do I write a vector? This vector is living in the Hilbert space HD, tensor product HD. This is the Hilbert space where it is living. Now, if there is an unitary, there is some operator u which is living in bipartite Hilbert space, then its vectorized version lives in the 4-partite Hilbert space. That we are going to write it and understand in this way. That let's see, there are the 4 particles, 1, 2, this is the 1, 2, 3, 4, 4 particles, and these 4 particles, there is a unitary operator. There is a unitary operator acting on particle 1 and particle 2, and the particle 3 and particle 4. 1 and 3 are maximally entangled, 2 and 4 are maximally entangled. You can see this, the state is being written in this way. U equals U1, 2, 3, 4. This is the maximally entangled state, this is the maximally entangled. Any general state can be written in this form. Or other words, what I am writing is, whatever I am writing is in the going reverse order, in the sense that any general state I am writing is in this form. This is the 4-partite state. What I need this four-parted state to satisfy is I want this four-parted state to be Ame state. That means absolutely maximally entangled state. That means 1 2 versus 3 4. It should be maximally entangled. So that row 1 2 should be maximally mixed, and 3 1 versus 4 2 also must be. These are the different cuts. Along this cut also it should be maximally entangled. And another one is 1 4 1 4 versus 2 3 or 3 2. This also must be maximally entangled. That is what the requirement I need. And we found out that the reduced density matrix of 1 2 system, reduced density matrix of 3 1, reduced density matrix of 1 4 turns out to be in this form: U dagger, U R1 U R1. I will be telling what this R1 and R1 and T2 are. These are called the matrix reshaping. Suppose, and of course, U is already taken to be U is unitary operator. If U is therefore row 1 2 is maximally mixed, that means that the cut 1 2 versus 3 4 is maximally entangled. If I want 3 1 versus 4 2 to be maximally entangled, similarly 3 2 versus 1 4 to be maximally entangled, what the requirement is that UR1 this must be identity and UT1 this must be identity. Then this state will form the Ame. Ame 4 states. That means absolutely maximally entangled 4 state. What is this matrix reshaping? This is the matrix. You take X sum 1 2 3 4 5 6 and I am making this. Okay. R1 which we have used here is one type of matrix reshaping. It's called 1 5. You can see this is 1 first I wrote 5 2 6. Make this column. Similarly 9 10. So this block is being made as a one column. Another block is made as another column. This is called the realignment. And similarly, this block is made the row 1, 2, 5, 6. So that's called the another realignment R2. And another one is called partial T1 and T2 are the partial transposition matrix transposition. Transposition in one subsystem. So this is also you can see here the block transpositions you can see. So T1 is the block transposition. So 9 this sorry this block is moved to here and this block is moved to here. So this is what the block transposition which is called the T1 partial transposition, and another one is within the blocks there is a transposition. This is the another one T2. So here you can see that. So these are the matrix reshapings. This matrix reshapings plays an important role in this characterization of four-party entangled state, which is absolutely which is nothing but absolutely maximally entangled state. Now, the question is, how do we construct these operators, and is there everywhere these Ame states exist? There are a lot of research, interesting research is going on in which where does the Ame states exist, for what dimensions Ame states exist, when it does not exist, and all other things. We will try to, for example, there is no 4-qubit Ame state. There is a well-known theorem saying that no 4-qubit Ame state. There was one open question regarding D equals to dimension 6 4-party Ame states, whether it exists or not exists, which has been recently solved. And like that, different states where it exists, when it is exists is a big interesting research field. There is a nice table uh, written by Felix Huber. He maintains that table. You can search in the Google Felix Huber Ame states where it exists and all exists. Okay, let's come back to our notion. What was the question which we begin with? There is a four-parted state. This is the operator which we are beginning with, and if this operator having said that if this operator after doing this type of realignment, that means there is a 4 cross 4 matrix, after you do this reshaping, after this doing this reshaping, whether it still remains an unitary operator. If it becomes a unitary operator, then the corresponding state is a 4 parties Ame state. In order to do that, there is a one interesting field enters. This field is called the combinatorial designs. These are called the combinatorial designs. So there are various fields enters in this one. One is combinatorial designs and entanglements and the classical codes and then quantum error correcting codes, classical error correcting codes and the diagrammatic methods, categories. I'll try to give the essence of all these things. Here I will try to construct those states, those unitary operators which remains unitary even in the after doing the matrix reshaping. Normally it won't remain unitary, only certain systems will remain unitary. What are those and how we are going to do that? Let's imagine there is a permutation operator. Okay, so this is a permutation. That means, for example, in the one dimension 1 2 3, if this is the your 1 2 3 are the elements, and if ask the permute these elements, you will say that 2 1 3 is the permutation. Now the permutation is defined in the two dimensional d cross d Euclidean product. Okay, so it is permuting like this: 1 1 goes to 1 1, 1 2 goes to 2 3. Okay, 1 3 goes to 3 1. This is what the permutation is. And the permutation operator, the one which permutes, okay, like is nothing but a unitary operator, where the permutation operator in each row and column only one of the element is 1, remaining all the elements are 0. This is what the permutation operator looks like. For example, very simple is swap. Swap is a permutation operator which swaps every computational basis. In general, the permutation operator is what you begin with ij, some computational basis. I am permuting the computational basis. It will goes to some other, something like, for example, if I begin with 1 5, it will goes to, if it is 5 is the number of basis vectors, then it will goes to something like 2 3, whatever it may be. Adjust. So this is one type of permutation. Now let's imagine d equals to 3. That means only 3 elements exist: 1 2 3. So the dimension is, it is a 3-dimensional object. For this 3-dimensional object, there are the 3 elements 1 2 3 and 1 1 1 2 1 3 2 1 2 2 2 3 3 1 3 2 3 3. This is how the permutation is being combined, and this is the permutation. 1 1 goes to 1 1, 1 2 goes to 2 3, 1 3 goes to 3 1. I'll write this matrix into K matrix and L matrix, where K is one first elements, just 1 3 3, see 1 3 3, 2 2 1, 3 1 2. This is also just second element, 3 1 2, 3 1 2, like I am just dividing this into the K matrix and L matrix. We prove that unitary remains after reshaping also unitary if and only if the elements in this form is such that over the row it must be distinct. No element should repeat over the row for the K matrix, whereas for the L matrix, no element should repeat over the column. You must have seen in your in the newspaper, there will be Sudoku columns. So this Sudoku is another combinatorial design, which we will be coming to. If this condition is satisfied, then UR remains unitary operator. Similarly, UT remains unitary if in this form K matrix and L matrix, over the row, over the column, it should be distinct like 1, 2, 3, and whereas the L matrix over the row, it must be distinct. If both ut and ur need to be unitary, that means the state has to be Ame state. What is the condition is that each this 3 cross 3 block matrix elements over the column and over the row must be different. This type of systems are called Latin squares in the combinatorial designs. And the two Latin squares forming another Latin square is what is called the orthogonal Latin square. Therefore, each orthogonal Latin square represents one Ame states, absolutely and maximally entangled Ame states of 4 parties. This is about the 4-party entanglement. Then you could ask why it is important and all other things, which I've already explained in some generality. But there is another place where it is much more important is in the many body theory, in the treatment of the many body theory. For example, if we have just I'll try to give the numbers. You see that if you have the 21 two-level system, this is the dimension of the matrix which you will be dealing with. If it is 3-level system, this is the dimension of the matrix which we will be treating. No numerical classical algorithms can work with this many number of dimensional system, and it's very hard to comprehend classically. And many body systems is everywhere in condensed matter, quantum computation, black hole physics, string theory, everywhere. How do we deal with this? That's where enters again these Ames and other things. And this is what the quantum computational circuits which we say. Let's say these are the your qubits. What I am writing, the legs of the vertices represents the qubits, and each one qubits or qubits, each box represents a unitary operator or gates, and it is evolving in this direction. And there is one concept: if this unitary operator is an operator such that u and ur both are unitary, which is nowadays is called the dual unitary operator. If this dual unitary is satisfied, then there are what happens, some diagrammatic calculation enables straightforward calculation of any two observable situating between any two spatio-temporally separate correlation function between spatio-temporally separated objects, and it can be calculated explicitly, and it just depends upon unitary operator acting on the two-body system. What is the usefulness of that one? This will provide one thing is to classification of the systems in some sense what is called ergodic hierarchy, more chaotes, and for example this is the non-interacting and non-ergodic. There are the phases of the systems, so it's becoming more and more chaotic, deterministic to more and more chaotic. More than that, what the recent proof says that if the unitary operators is built from this type of operators which are called the dual unitary operators, which over the long time provides the computational advantage that no classical computers can achieve. That means this setup in which the unitary is building from where the unitary gates are such that its realignment, its reshaping is also unitary, those circuits overperform the classical computer. This is a recent result by Fuzzy. That's where it is important. And interestingly, what are these dual unitary operators, or the operators which is giving maximal absolutely maximally entangled state, is again connected to entanglement of operators, not just entanglement of states. Till now we explained only entanglement of states, and this is entanglements of the operator. And this dual unitary operators, which forms the, which is used to explain absolutely maximally entangled state, is the operator which is having the maximum entanglement. And another one, which is the last concept which I am trying to explain, is the entangling power. So all the gates which we use in our computation, we need to ask what is its entangling power. That means how much average entanglement that it produces. And what the Ame states which we use, that Ame states is nothing but the state which is having the maximum entangling power. So from that, there is those unitary operators which is having the maximum entangling power, and those unitary operators from which the four-party absolutely maximally entangled states can be formulated. These are the one are most chaotic. This forms what is called the Bernoulli system in the many body systems, and those are the most chaotic system and most difficult to simulate it in classically, thereby giving rise to quantum advantages in the quantum computational setup. Okay. So these are the few ideas, concepts which I wanted to connect. Let me repeat briefly whatever the ideas which I have explained. I begin with the two-party system and explain what is entanglement and how you define this entanglement and all, and then where it is been, why it is important from the physics perspective. Starts from the Epr paradox and then Bell's experiment, and why it is important. It is important to produce it in security aspects and randomness generation and all other things. When we go to the higher dimension, a higher number of parties, especially four parties, we define what is mean by absolutely maximally entangled state, which are the states which remains entangled in any bipartition. So how do you construct those states? Those states are constructed from the operator to state mapping, where you have an operator, and those operator you reshape into a vector, so that you will get this state. What should be the condition on this operator u that will guarantees the state to be absolutely maximally entangled state? That condition we studied, and how to construct those operators starting from permutation operators is what is explains the theory of quantum combinatorial designs. And these are the states which is essential for quantum error correcting codes, and how to construct quantum error correcting codes comes from this quantum combinatorial designs. And the unitary operators, which if the many body circuits is being built from this unitary operators, which are most chaotic in its quantum chaos sense, and there is a recent result that this cannot be simulatable in the classical computer, which gives the complete advantage over the classical computation. And then the power, where does, if you ask where does the power comes from, this power comes from the entanglement of this unitary operator itself. Whenever the operator entanglement is maximum, then it is giving some power. And if along with the operator entanglement, if it is entangling power, another measure of how efficient an unitary operator in creating entanglement is, if that is being taken into the consideration, then those circuits which is built from this unitary operators are most chaotic, and it's called the Bernoulli circuits, and this gives rise to this is the most chaotic circuits and most difficult to simulate even classically also, which gives the computational advantage. So in this way I try to, and this is been calculated using some diagrammatic formalism. So there are many interesting mathematical frameworks also connected: classical designs, quantum designs, diagrams, category theory, and then Hilbert space. Okay, so that's all from my side. Thank you. Thank you. Any questions or any comments you have? These are the few references, very few references is what I am giving here. Many more. Ganesha and Bhartini Kosh, and we wrote some 2 papers. So, a lot of the things which I explained here, except Bell's experiment and other things, you can find it here. Okay, if there is no questions, I'm concluding. Thank you. Organize.
Yeah. So may we, I mean, ask some participant for any queries?